Thanks for tuning into this Revision Zone Maths video. In this video, we'll be calculating derivatives of non-trivial functions. Now, in the video series on differentiation, we've seen a lot of work already, and in particular, we've seen lots and lots of rules and lots of derivatives of standard functions. So I thought this will be a good place to basically go through examples of lots of those rules mixing in with one another, because up until now, we've only really seen those rules used in isolation. Since there isn't really anything too new, I've decided just to already write things out and just talk through it in the interest of time. So let's think about example one. This is a fairly standard quotient, obviously. We've got log x in the numerator and tan x in the denominator. So I should say normally I would have to say, or I should actually say, the fact that this function is only defined for values of x for which tan x is not 0. But just because of convenience, I'm taking that to be an implicit fact and not stating that explicitly. Okay, so obviously our function is of the form u over v. It's a quotient, and we know that the quotient rule allows us to differentiate functions which are quotients. So we're going to have to define our u to be log x, our v to be tan x, and then we need derivatives of u and v respectively, and then we're in a position where we can use the formula. Okay, so since our u is log x, we've already seen into the previous videos that its derivative is just 1 over x. Again, the caveat that x can't be 0 must be the case here. And since our v is tan x, then its derivative is sec squared x. We've seen that before as well. So now we just put everything into here. So we get v du dx, but our v is tan and du dx is 1 over x. So that's what we have, tan times 1 over x. Then we have a minus, and then we have a u dv dx, but our u is obviously log x, and our dv dx is sec squared x. So we have log x sec squared x. And then lastly, we have a v squared in the denominator, but our v is tan, so we just have tan squared in the denominator. So at this stage, when I move on to the next line, we just have to be able to tidy things up, really. In fact, that's all we do from sort of this point onwards after we've already substituted. So obviously tan x times by 1 over x is the same thing as tan x over x. But when we have that, I need to get a common denominator with the term on the right-hand side here in the numerator. So I multiply top and bottom here by x, so I get a fraction over a fraction. But then we obviously know a standard result, which is if you've got something of the form a over b over c, that's the same thing as a over bc. Okay, so that's just standard algebra. So using this, we can basically jump from this step to this step. So our b happens to be x. So you see the a and the c remain as the ultimate numerators and denominators, but the b switches from being the denominator of the first part to being the denominator of actually the whole thing. So the x can just come down here, and that's precisely what we have here. So example 2 is more like the sort of function that we would not have been able to easily differentiate before, and precisely the sort of thing we want to be considering in this video, which is we have a quotient, but it's not quite a standard quotient because the numerator itself is not just one easy function, it's actually a product. So somehow we've got to use the product rule together with the quotient rule at the same time. Okay. So before I jump into describing the solution, I would just point out that in the interest of convenience, I've not written out the fact that x can't be 0 here. We should always be careful whenever we write down quotients just to make sure that denominator is not going to 0. So let's get started. So since we've got something of the form u over v, we take our u to be sine x cos x, and we take our v to be x squared. The derivative of v with respect to x, dv by dx is just 2x. That's fairly straightforward. The derivative of u with respect to x, du by dx in other words, well, we can certainly work it out, but it's not too obvious just to sort of write it down in the first instance. We've got to apply the product rule on this. So I'm going to just put a question mark there and sort of work that out as a separate calculation. Okay, but the problem is, until I work that out, I can't go and actually apply the quotient rule. Okay, so let's work out the derivative of this function here. So we need to use the product rule. We know that the product rule, if it's written in Newton's notation, if the capital F is equal to a product of two functions, lowercase f and lowercase g, then its derivative is basically you put down the first function, you multiply by the second function, then you put down the second function and you multiply by the derivative of the first function, and then you add them, and that's the derivative of your overall function. So in this case, I'm going to take my f to be sine x and my g of x to be cos x. Then we know that f prime, lowercase f prime is cos x and lowercase g prime is minus sine x, and we basically put those things into here. So I write down the sine, I multiply by the derivative of the cos, which gives me minus sine, and then I write down the cos and I multiply by the derivative of the sine, which actually gives me cos. So here we've been able to work out our du by dx, and now we can put all of that into here. So first of all, I want to write down v times by du by dx. But what's my v? My v is just x squared, and my du by dx is this function here. So it's going to be x squared times by cos squared minus sine squared, because this thing here is basically minus sine squared plus cos squared, but that's exactly the same as cos squared minus sine squared. So the first part of the formula makes sense. Then the second part of the formula is u dv by dx. Now my u is sine x cos x, and my dv by dx is 2x. So it's going to be sine x cos x times by 2x. And obviously that minus is there just from the minus in the formula. The denominator of v is, of course, just x squared, so we just have x squared all squared, okay? So now it's just really a matter of simplifying. So far there were x squared to the power 2x's there, so there were x to the 4x's there, and since we can take an x from here and an x from here, one of the x's goes away, so we only actually have 3x's in the denominator as a power. Uh, and we're basically left with this, and the final step going from here to here is actually using some standard identities. So perhaps I can sort of write them in from the trig part of the A-level syllabus. We could go away and sort of figure out that actually cos squared x minus sine squared x is the same as cos 2x. Okay. If this identity is new to you, you might want to go away and sort of look it up in a textbook. Likewise, I can actually say 2 sine x cos x is actually the same thing as sine 2x, right? This is another standard identity, and the same comments that I actually made for the first identity would apply here. So knowing those identities, we can just basically write out our answer in a much more simplified way, and we're done. Example 3 is another quotient. The slightly more interesting thing here is the numerator is actually a function of a function. So I've got e to the power of a trig function, right? So as always, I should say caveats about cos x not being 0 and so on. For convenience, I've just left that out. We can just jump straight into the actual calculation here. So because I have a quotient overall, I'm going to have to use the quotient rule, but obviously my u has to be the numerator and my v has to be the denominator. Now, I've got to differentiate both these, and we can differentiate the v, that's no problem. Cos just differentiates to give us minus sine, that's a fairly standard result. But e to the tan x usually in the past would have taken us a bit more work, and indeed we prove the standard result of the form that if you've got e to the power of f of x as a function, then to differentiate e to the power f of x, the answer is just going to be, it's going to be e to the power f of x, but you've got to multiply by the derivative of lowercase f. Because we have this, we can, life is very easy because we can just say, well, take f of x to be tan x, and my uh, e to the tan x just becomes e to the f of x, right? And now I can go and use this result. So when I differentiate this function now, I'm going to get f prime x times by e to the f of x. But the derivative of tan is sec squared. It's a standard result, which we've already shown in previous videos. So the derivative of e to the tan x is just going to be sec squared x e to the tan x, right? And now we can basically just put every single thing in to the formula. So we have v du by dx, but our v is cos x, our du by dx is sec squared x e to the tan x. So we just have cos x times by sec squared x e to the tan x. That's the first part. The minus is obviously just carried over, and then we have u dv by dx, but our u is just e to the tan x, and dv by dx is minus sine x. So it's going to be e to the tan x times by minus sine x. And of course, the important thing here is the minus out in the middle and the minus to the far right combine. And the other interesting thing is the cos x and the sec squared x actually simplify to give us the sec x, and we can perhaps just quickly see that, because if we have a cos x and I multiply by sec squared x, but of course sec is just 1 over cos, so sec squared is just 1 over cos squared, right? So one of these causes is going to cancel with one of the causes in the denominator because I've got two causes being multiplied in the denominator. So only one cause is going to survive. But obviously using the definition of sec again, I can just rewrite this as sec x, right? And of course, these are technically identities, right? But we don't normally write these down when we're doing this sort of work, so I won't write them down. Yes, so since we know that cos x times plus sec squared x is just sec x, we can just write that in and the entire thing looks so much simpler, right? The only thing worth doing here might be to factorize out the e to the tan x. So we can take that out, and obviously that denominator applies to the whole thing. So in fact, we can write all of this thing here in a much nicer way as all of this thing. Example 4, we have another rather interesting looking function. Of course, we want to differentiate it, and in the past, we would actually find this sort of thing a little bit hard because our go-to approach might be to be able to expand everything out and then differentiate each term, but that would be a lot of work and not really recommended because there's also a high chance of making a mistake when you're doing something like that. And certainly that should not be attempted on an exam paper just because we will just not have any time to be able to do that sort of thing on an exam paper. So here we're going to use a few rules simultaneously to be able to work this out without actually expanding this. So the first thing to notice is this is actually a product. I can think of this as a function in itself, and then I can think of the other thing as a function in itself, right? So provided I can differentiate this part and the second part, I should be able to use the product rule to differentiate the whole thing, okay? So that's what I say y equals uv, and our u is just 2x minus 1 all to the power 5, and our v is just 3x plus 4 all to the power 4. But now differentiating the u and the v is a little bit awkward because again, we might be tempted to say, well, we've got to expand this out, right? So yeah, we can do that. And in fact, if we did that, already we would notice that that alone would be so much more simpler compared to expanding the whole thing out here to begin with, right? Because here we've got to expand something to the power 5 and then something to the power 4. So we get 6 terms here, we get 5 terms here. And then when we sort of cross multiply each term, and we're going to get 30 terms coming out. Whereas when we expand this, we don't get 30 terms coming out. And when we expand that, we certainly don't get 30 terms coming out. So already, if we were to treat these things separately, life is a lot easier. Having said that, we're not going to expand this and we're going to go to a standard result. And the standard result is if you've got a function to a power where the power can be any real number, then you can differentiate the overall function by basically multiplying by the power, taking away 1 on the power, and then multiplying the whole thing by the derivative of the function on the inside, right? And there's obviously another way of writing that, but it doesn't really matter which way you write it, provided you don't make a mistake. So let's jump in. So we're going to use the standard result twice. We're first going to apply it to u, and then we're going to apply it to v, right? So case one is we're going to take our lowercase f of x to be 2x minus 1 and our n to be 5, right? So we've got something like that basically. So when we differentiate, it's going to be n times by f prime times by f to the power n minus 1. So our n is just 5. Our f prime, so 2x minus 1 differentiates to just give us 2. And then our f is obviously 2x minus 1. And then the power we want to be 1 less than n. Well, our n was 5, so 1 less than 5 is 4, okay? And obviously simplifying that, that just gives us 10 times by 2x minus 1 all to the power 4. And then case 2, so now we redefine our f, our lowercase f here, and now we take our lowercase f to be 3x plus 4, right? Which is basically that thing on the inside of the bracket there. And we take our n to be 4, which means v is basically the same thing as f of x to the power n for our given lowercase f and our given n being 4. Again, differentiating this, it's going to be n times by f prime. So our n is 4, our f prime is the derivative of 3x plus 4, which is just 3, and then we multiply by f of x, which is obviously 3x plus 4, all to the power 1 less than n. Well, our n is 4, so 1 less than n is 3. So once we've got that, we just basically multiply things out. So we're going to have 4 times 3 to give us 12, and then the bracket is just going to come along for the right. So we've now got Ru and V together with du by dx and dv by dx, so we just turn to the product rule. So our u is obviously 2x minus 1 all to the power 5, and our dv by dx is 12 times by 3x plus 4 all to the power 3, so that's what we have here. Now we have to turn attention to the other part, which is v times by du by dx. Well, our v is just 3x plus 4 to the power 4, and our du by dx is obviously 10 times by 2x minus 1 all to the power 4. So we should have that times by that, which is exactly what we have there. Okay, that's precisely the same thing. So now that's basically our answer. So we've been able to write down our answer entirely, but the only thing is that's not in the nicest form. So we just want to be able to tidy things up. And one way of tidying things up is we actually notice that in both the terms we actually have, because we have two terms, there's one term there and then there's another term there, we actually have same sort of things repeating. So we've got a 3x plus 4 to some power here and a 3x plus 4 to some power here. And then we've got a 2x minus 1 to some power here, and we've got a 2x minus 1 to some power here. So we can actually factorize a 2x minus 1 to some power and a 3x plus 4 to some power. And once we've done that, we find that we actually get left with a factor of 2x minus 1 on the left and a factor of 3x plus 4 on the right, okay? And if you think about the powers, then that makes perfect sense, right? Because we have a power of 5 here, but only a power of 4 here, so we must have best have a power of 1 left on this side. But then for the other term, we have a power of 3 here and a power of 4 there, so we best have a power of 1 left on this side, which is exactly what we have there, right? And obviously these numbers are just going to come along for the ride. So once we've got that, already this is so much easier than what we had above there, but we can still make this simpler. There's a factor of 2 there, and there's a factor of 2 there, so I can take that out, which means obviously how many 2's go into 12? Well, 6 of them, so I have a 6 there, and how many 2's go into 10? Well, 5 of them, so I have a 5 there. So at this stage, as I say, the 6 goes in, so a 6 times 2 gives me 12, and then 6 times 1, this should actually give me 6, so I should actually have negative 6. So I must have rushed that, right? And then the other one, obviously, we're going to have a 5 times 3 gives me the 15, and then a 5 times 4 gives me the 20. And obviously, now my answer is going to change a little bit because when I actually combine these, what I'm going to have is I'm going to have 12x plus 15x, which of course is 27x, but minus 6 plus 20 is actually going to give me 14. So I can just write that here. And that's basically the answer because everything else are just they're just factors and they all just come along for the ride. So we've been able to work out our final answer. Example 5 is actually a fairly nice and easy example. We have a function which is basically combining a product together with a function of a function. So that thing there is somehow a composite function because log is a function and then sine x is itself a function and sine x is actually inside the log function. So we've got a function of a function times by another function. But obviously, because the overall structure is a product, something times by something else overall, then I turn to the product rule, but I need to know the derivatives of each of the functions that I'm actually going to define. So it's natural to take u to be x and for v to be log of sine x. Obviously, du by dx is easy. That's just 1. But dv by dx, we need to use a standard result to be able to work this out. So I've not written the answer there and I've quoted a standard result, which is if you've got a function, which is basically obtained by taking some lowercase f as a function and then taking the log of that, then to differentiate the overall function, in other words, this thing here, what you basically do is you say, I'm going to take the lowercase f function, and that's going to be my denominator, and then the numerator is going to be lowercase f differentiated, of course, right? And I should say here, the standard caveat applies that, values of x for which the denominator vanishes are not allowed. I've not said that just out of sort of convenience. But this result was actually proven in one of the previous videos, so do feel free to go back to the playlist on differentiation year 2 and see how this has worked out if you're not too sure where this came from. Okay, so just applying this, we take our f of x to be sine x, and then log x sine x just becomes log x f of x. But of course, we know how to differentiate sine x, which is we just get cos x. That's a standard result. Therefore, we can now work out dv by dx, which is just f prime x over f of x, which is cos x over sine x, which is nothing other than the definition of cot x. So now we have uv, du by dx, dv by dx, and we can just put everything into that formula for the product rule. So we need u dv by dx, which is u times by which is x times by cot x, which we have there. And then we need v times by du by dx, which is just log sine x times by 1, which is what we have there, log sine x times by 1. And of course, there isn't really anything you can do here. This is as simple as it's going to get. So we just basically write that down. So it's a fairly straightforward example. So the next example is actually something fairly standard. We've seen this sort of thing in the past where we're given x as a function of y and we're expected to find out dy by dx, right? So I should emphasize we don't want dx by dy, we still want dy by dx, but we're given something which is on face value sort of not conducive to doing the sort of calculation that we're asked to work out. But obviously the key idea is there's a result, and the result says if you want to work out dy by dx, you can just work out dx by dy and then say 1 over dx by dy, and that is guaranteed to give you dy by dx, right? Now, why is this true? We covered this in one of the previous videos. Feel free to go back and take a look at it. And obviously at this stage, it's got to be said that all the standard conditions where dx by dy can't be 0 and so on and so forth apply. I've just not sort of made a big fuss of them here. The thing here is obviously this is a very standard sort of thing in that we've done these sort of questions before, and so you may think, well, why are we covering this? The point is the result is quite important. Indeed, it was the only way we could work out the derivative of things like log functions and inverse sine and cos functions. So it's a fairly useful thing, and I just wanted to make sure that actually it doesn't slip our memory. So let's just jump in. So before I differentiate, I want x explicitly as a function of y. So I divide both sides by 4 to be able to have this thing here. And now I can just go and differentiate each term. So of course, because these are in y, so when I do the differentiation, it's going to be with respect to y. But what am I differentiating with respect to y? Well, it's nothing other than x. So dx by dy is just going to be a quarter times by log y differentiates to give me 1 over y, and y cubed differentiates to give me 3y squared. So that's my dx by dy. And there's nothing to do but to basically use this result and just to replace dx by dy by the entire thing here, which is what I've done at this stage. So to tidy this up algebraically, we can just combine the first part of this fraction to the second part, which means multiply top and bottom of this by y. So I get 3y cubed over y, which is exactly the same as what I have here. And then a quarter multiplied by that, well, nothing's going to happen. The 4 is just going to come to the denominator. And finally, if we have something of the form 1 over a over b, we know that's the same thing as b over a, right? That's just standard algebra, and that's precisely what's happened in going from here to here. And we've got our answer. There's a remark which says, now if I wanted to use this to work out the derivative at some point AB on the curve, all I have to do now, because this thing here is in terms of y, I basically evaluate dy by dx at y equals b. Okay, so in the past, we would normally put in the x coordinate, so x equals a, but in this case, because our derivative is completely written in terms of y, we won't put in the x coordinate, we would actually put in the y coordinate, right? And obviously it's going to give us 4b over 1 plus 3b cubed. Example 7 is a very straightforward application of the product rule. It's a very nice thing to look at because the function looks just so nice. It's something like x cubed times by 3 to the power x. So it's this funny snake thing happening here where you start with an x, then you go to a 3, then you have another 3, then you end with an x, right? It just looks very pretty. So we want to differentiate this product rule as always. So we say u equals x cubed, which is the first part here. And then we say v equals 3 to the power x, which is the second part here. And obviously we can differentiate each one of these directly. So x cubed differentiates to give me 3x squared. So that's my du by dx. And 3 to the power x, we work this out. There's a standard result which actually said if you've got y equals a to the power x, then dy by dx is equal to log a times by a to the power x. So we saw this in one of the earlier videos. Do go back and take a look at it if you're not too sure. And there are obviously conditions on a. A has to be sort of positive or whatever, right? In this case, that's fine. So 3 to the power x differentiates to give us log 3, just as we have here, times by 3 to the power x, right? So we now just stick all this into the product rule formula. It's u div dx, so it's going to be u times by that. So it's going to be x cubed times by log x times by 3 to the power x. And then it's going to be v du by dx. So it's going to be that times by that. Okay, which is going to be 3x squared times by 3 to the power x. So 3x squared times by 3 to the power x. So you may notice actually to do the product rule, we somehow went across, and this is something that some teachers teach, which is to lay out your answers in this way and not even, you don't even have to remember the product rule, right? You can just write down what the answers are going to be because you know if you've laid things out in a way where you've got uv and then you've got their derivatives under them, you know that you're just going to multiply across and then you're going to add them up, right? Which is exactly what we've done here. So that's fairly straightforward. Once we've got this, this is essentially the answer. The only thing perhaps worth doing would be to simplify it. And we see that we've got 3 to the x here, we've got 3 to the x here, so we can certainly take 3 to the x out. And then we also see that we've got an x squared here, but we've got an x cubed here. So we can actually take an x squared out of here and from here, which means we're left with an x for the first term, and then we're left with a 3 for the second term, but then the log 3 remains as part of the first term. So we have our answer looking lovely just here. So we can now move on to the next example. So example 8, we again have a rather interesting looking function. It's a composite function because we've got a function and then we've got a function inside that function. But the slightly funky thing here is we've got the exact same function. So we can actually do this lots of ways, but let's just do it using a standard chain rule application just to sort of bring your mind back to the fact that just because something looks horrible, it doesn't mean that you need multiple different rules. You know, it may be the case that one of the rules that you've got will just work just as fine. So RU, if we take all this thing on the inside to be RU, then obviously u is log x, but then y becomes log of u. Okay, so we've got our u and we've got a description for y. And to be able to do the chain rule, we need to differentiate both these things. And this is where the interesting thing happens because the answer looks very much the same because of course the function is very much the same, right? So du by dx is just 1 over x and dy by du is just 1 over u. And the chain rule tells us this statement here, which is if you want to go from y to x, you can go from y to x via u essentially, right? So we write down dy by du, which is just 1 over u. Then we write down du by dx, which is just 1 over x. And that's it, really. So this essentially is our answer here for our derivative. But obviously, we don't want it in terms of u and x that have combined. We want it purely in terms of x. So we go back here and say, well, what is our u? It's just log x. So we replace that u by log x, right? And so the answer is 1 over x times by log x. And of course, when I did these derivatives, I should have said something about, you know, the denominator can't be 0 or whatever. And the same thing is going to be true here, but just out of convenience, I've just left that out, taking it to be implicitly understood. So that's basically that, and that's the answer. The alternative way of doing it is just using a standard result that we know about logs. We've already seen this in this video, which is if you've got log of some function, then obviously you can differentiate the entire thing by basically saying 1 over the function, right? So 1 over the function multiplied by that the function differentiated, which is exactly what we have there. And again, the standard caveats about you can't take log of negative numbers and so on apply, and you can't have things in the denominator, which is 0, apply here, which I've just sort of skimmed. And if you take f of x to be log x and just apply that formula, you can get the same answer again. Okay, I'll leave you to check the details. Example 9. So here we have a rather interesting looking quotient. We're not going to need anything more than the quotient rule here, but this is precisely the point, which is even when you just need a standard quotient rule and not multiple applications of lots of different rules, you can still have something which is actually quite messy to work through. So again, standard sort of thing. So we say our u is sine x cos x, which I say here. And then we say our v is sine x minus cos x, which I say here. And we can differentiate these very directly. So sine differentiates to cos, cos differentiates to minus sine, and obviously sine differentiates to cos, and cos differentiates to minus sine. So that minus and the minus that would come out from the derivative of this cos combine to give me a plus. So we basically have u du by dx and we have v dv by dx. And then we just go straight to the quotient rule, right? So I say v du by dx. Well, that's my v, and that's my du by dx. right? So I basically write these things down. So sine x minus cos x minus sine x. So sine x minus cos x minus sine x, and it's being multiplied. And then it's u dv by dx, which is sine x plus cos x times by cos x plus sine x, which is exactly what I have here. Sine x plus cos x multiplied by cos x plus sine x, right? And obviously the minus is just going to be in the middle. And again, I would like to maybe highlight that if you actually notice what's happening, we're still going across. So we're still doing like this sort of thing. So we've got v and du by dx, which is the first term here, and then we've got u and dv by dx, which is the second term here. But the thing to keep in mind now is there's a minus in between the two, which is how it's different to the product rule, of course. And the other thing is order matters. So I have to start with the v. So I have to do this first, write that down, and then I've got to do that second, write that down, and then take away the answers, right? And then divide the whole thing by v squared, but v is of course just sine x minus cos x, so you can just write that down and square it. But obviously, in highlighting this sort of way of thinking about it, what I'm saying is you don't have to remember this formula. You just have to remember, or maybe just get into the habit of writing things down in a particular way, and knowing that once you've written it down in that way, you go this way, write down the answer, you go that way, write down the answer, subtract them, then you write that squared, okay? So that's what we get. That's what we get. And now we have to expand the numerators and simplify. And this is where it's going to be a bit more work. So I've done it in a different color just so people can sort of follow. The sine times by the cos gives me sine cos, and then the sine times by the sine gives me minus sine squared. And then the cos times by the cos gives me the cos squared, and of course the minus just comes along for the ride. And then the cos times by the sine gives me sine cos, but the two minuses cancel to give me a plus, right? So this is the first set of brackets expanded. And then the second set of brackets, exactly the same thing. The only difference is here I had two negatives, but now I have two positives. So actually it's going to be the exact same answer as what I had before, but now there's going to be no negatives inside. So I'm just going to have positives. And you can sort of check for yourself that actually the terms marry up perfectly, right? So I get sine x cos x, sine x cos x, sine x cos x, sine x cos x, and then minus sine squared minus cos squared plus sine squared plus cos squared, okay? So of course there's a minus in between, which is coming from that and ultimately that. But at this stage, we notice that we can use sine squared plus cos squared as 1 twice. So this thing here just gives me minus 1, and this thing here just gives me 1. So since the whole thing in green is being taken away from the whole thing in blue, what we're actually going to have is we're going to have effectively something like this. We're going to have this cancel with that, and we're going to have this cancel with that, leaving us just with minus 1 from here, and then the takeaway, and then 1. So negative 1 take away 1 is just negative 2, so I have negative 2, right? And the denominator I've just left alone. So I've actually got an answer for the overall function that we were trying to differentiate, and I hope you would agree that this is a rather nice looking thing. So the final example is actually a composite function. So actually it's a chain of composite functions. So I've got a square root function, then I've got a sine function, then I've got another square root function. So I've actually got three functions there. And if I really wanted, I could actually do something like this. I could go away and do dy by dx is equal to dy by du times by du by dt times by dt by dx, right? By making suitable choices for what my u is going to be and for what my t is going to be. So I might want to say u equals say sine of root x, and then I might want to say t equals root x, right? So u actually happens to be sine of t. So if I make these choices, I can actually just differentiate this thing using the slightly extended chain rule. But obviously I've not done it this way. I've laid it out in a slightly different way where I've used the standard result in conjunction with a chain rule. But obviously the chain I've used is a much smaller chain just to make life a little bit easier, right? So let's think through this. So we've already seen before that if I've got a function capital F, which is obtained by taking a function lowercase f, and raising the whole thing to some power n, where n is some real number, then I can differentiate my initial function, in other words, the whole thing, by basically multiplying by the n and subtracting 1 on the end, and then multiplying the whole thing by the derivative of the lowercase f, right? Which is exactly what we have here. So if I take my f of x to be sine of root x, I can just write down, so I hope you would agree that we can just express the square root as a power, so we can rewrite our y in that way. So in fact, my y does happen to turn out to be something of this form. So using this result, we can just say it's just going to be a half times by 1 less than a half as a power, which is minus a half, and then the f of x is just going to be there, and we need the derivative of f, right? So we know what f of x is, it's just sine of root x. So indeed, we've actually worked out our derivative entirely, provided we can just differentiate the function that we've defined as f. And of course, we can differentiate this function because we can just go to the chain rule, right? So I can say let u be equal to root x. So my sine of root x just becomes sine of u, which is what I have here. But of course, that's what we defined as our f of x. So my f of x is now sine of u. But this is exactly the point, which is my u as a function of x, right? Which is what I've said here. So I've actually got a chain going on there. And so I want to use the chain rule. But to be able to do that, I'm just going to say, let me switch from using Newton's notation to being Leibniz notation. So I'm just going to introduce a new symbol, v, and of course v is nothing other than f of x, but I'm just calling f of x v for convenience. And then now v is a function of u, and u is a function of x, which is what we have here. So I can go into the chain rule and say dv by dx, because v ultimately is a function of x, is the same thing as dv by du times by du by dx, right? So the chain is being made with respect to the u here, and we can just go from v to x directly. But we can do all of this in sort of in quick succession because our v is sine u. So dv by dx is the derivative of sine with respect to u. Well, that's just cos u. And our u is just x to the half. So du by dx is just a half x to the minus a half, right? So we're basically done. The only thing we need is we need to write down our answer in terms of x and not in terms of u. So I replace my u by root x. And once I've got that, I put this back into the initial formula, which we had there. So it's just the same thing as a half sine of root x all to the power of minus a half times by the thing I worked out, which is a half x to the minus a half cos root x, which obviously can be simplified because the negative means I'm going to have a fraction. I'm going to have things like 1 over. The half times the half gives me a quarter, which is the same thing as having 4 in your denominator, and the x and the sine root x can be combined because they have the exact same power, right? So I'm basically using something like this, which is a b to the n is equal to a to the n b to the n, right? So I'm using this result to be able to say my n is minus a half, and that's my a and that's my b, so I can go backwards and combine them to say ab to the power n, which is what I have here, okay? So basically, we've been able to work out the full answer, the entire derivative to that messy looking function that we actually had to begin with. And I hope you would agree that it's useful to see how all the various ways of thinking about these sort of things can fit together and give you a better understanding of how to do some of these calculations. So with that, I'd like to bring this video to an end. We hope you found it useful. If you did, please do hit the like and subscribe buttons. Do leave a comment in the comment section as always, letting us know what you would like to see more videos on. Thank you for watching, and we will see you in the next video.